Good morning from here in Paris. Thank you for joining us for today's Siemens Global webinar. My name is Caroline Maître, and I will be your host for this event. I would like to thank you all for joining. Today's topic, we will be looking at how to estimate your tooling cost accurately, accelerate and optimize your product design processes, and tool costing in mold, tool, and die making. I am delighted to welcome as our speaker today, Mr. Peter Jochen. So I will give a very brief bio of the speaker and we will be ready to start. So before joining Siemens, Peter worked as a tooling designer and as process planning and cost engineer for stamping engineering for different automotive companies like BMW and GM. After joining Siemens, he was responsible in the service organization for Teamcenter product cost management trainings, and since 2018, he's responsible as Global Portfolio Executive to manage and develop the portfolio business for Teamcenter product cost management worldwide. All right, so without further ado, I would like to hand over to Peter.
Perfect, thank you very much. So, accurate cost calculation with Teamcenter tool costing and annex feature to cost for tool makers. This slide shows you the three major capabilities that we offer with Teamcenter product cost management: product costing, tool costing, and profitability calculation. Teamcenter product costing provides an enterprise-wide platform for creating and managing calculations and captures the company's internal costing expertise centrally. Product costing uses the methodology of classic overhead calculation based on a bottom-up approach. This approach is based on a detailed product structure and defines the use of material and process costs. Different manufacturing processes can be defined and evaluated in detail with the integrated cycle time calculator. With Teamcenter product costing, customers can receive the best design and manufacturing concepts of their products. With Teamcenter tool costing, customers can calculate and manage cost of tools, molds, and dies, which are required for multiple technologies in discrete manufacturing, for instance, injection molding, die casting, or stamping. As mold and dies are complex in terms of design, and manufacturing this approach would require very deep knowledge of the user, as well as very high efforts and time. For that particular reason, Teamcenter tool costing uses the more automatic methodology of parametric 3D-based costing. Cost estimates are based on parametric models which consider the specific tool type, the geometrical dimension of the part the tool is made for, as well as cost profiles for tool shops. With Teamcenter tool costing, customer can create valid tool cost calculations faster and with detailed cost breakdowns. Tool costing can be run standalone or fully integrated with Teamcenter product costing on a common platform. With the profitability calculation in Teamcenter product cost management, executives can secure product investments by predicting future unit costs and prices over the entire product lifecycle. They can transparently break down annual costs, revenues, and cash flows and provide the basis for relevant indicators such as internal rate of return, net present value, and payback periods. Using the discounted cash flow calculation, they can determine the profitability over their projects and compare projects to make the best investment decisions. The challenge in tool making have significantly increased over the last years. More and more calculations have to be made in a shorter period of time. Product complexity has increased, and more variants have to be recoded. Resource expertise is limited, but the demand for detailed offers increases. The customer requires more transparent cost breakdowns, and they spread the inquiries to more and more suppliers. Teamcenter tool costing allows a parametric calculation of various tool technologies, such as injection molding, high-pressure die casting, progressive dies, transfer dies, and as well line dies. This slide shows you the process of the parametric calculation. As a first step, the tool technology must be selected. After that, the part geometry needs to be described. This can be done either by analysis of the 3D data or by manual input. The selection of profile and location allows the consideration of pre-configured information, such as specification, manufacturing technology, and hourly rates. This information can be configured by the user, but also preloaded profiles and locations are provided by Siemens. The result is a tool cost calculation in a degree of detail that allows flexible generation of cost breakdowns meeting industry standards. For our tool calculation, we usually use 3D feature recognition via an X feature to cost. This 3D analysis works for molded parts, and we are able to identify all required technical features, like undercuts, ribs, insert areas. Furthermore, we can identify core and cavity as well. An X feature to cost tells us dimensions. For the stamping area, an X feature to cost identifies bending and trim, cutting areas, as well as the areas for embossing or drawing. Now I would like to show you how we do that. Here you see our tool costing. At the first tab, you have all the options how to admin the software. On the left hand, we have our Explorer. Now we have here the project folder. We open a new project, and we're using a new part. We can use a new tool. We can use geometry or profitability or variant calculation. And we want to create a new tool, which we have done now. On the right-hand side, you see our Explorer, where we can search for different items. Here now we have our tool technologies out of the box, like die casting, foaming tools, multi-component injection, prototype injection, standard injection, or further down, stamping and bending tools. Okay, let's start with the standard injection. Now we give our new calculation a name. We call it tool calculation 1, and we simply say accept. Now we want to create a new tool, and the calculation source is paramedic. As you see, we can load an Excel file, we can link an external program, or direct input, or a cost breakdown import. But today we want to use the paramedic calculation. Now we accept that. System is loading the data. Now we get rid of the windows which we don't need. We're hiding them. So we have here our basic data. This is the designation, tool technologies, and we can file attachments. We can either import any files or we can link files. And in the geometry tab, we have the option to link 3D files, which we are doing now. Loading a part, selecting it, and they open, and now click Analyze. And now an X fires up. And here's our part now. Now we're using the molding application from feature to cost. We're starting now. And the system already has recognized its body. And now we can specify the orientation by using the manipulator or the axis system. And you can change the location by simply dragging and dropping the axis system. So if you want to do it an easier way, we just simply click on the Z-axis, select the face of the part, click on it, and automatically the Z-axis orients it perpendicular to the face, changing now the direction because we want it in the other way. Double click on it, and now we have the correct setup for our tool. Now we are hitting the Analyze button, and the system automatically identifies the part dimensions and the attributes, and we can export the data to a desired folder. Now we have here the undercut already identified. We see here some undercuts which we need a slider with. It's in X plus direction. That's the undercut. We can change the side direction if we want to do that. We can change the complexity. Right now we're saying, okay, that is a rectangular slider, medium complexity. Then we can say it's a standard, it's a bird one, or is it difficult to access, a standard, and we can change the actuation. Should be an angle pin with a horn pin, with a mechanical locking system, which leave it to the standard. And now we want to add the other undercuts because we want to have that on one slider. We don't want to have 4 sliders for that. Now we're using that. Just say, okay, we're going to group it. There's now one group. Contains all the undercuts. Now we see that the surface, the mating surface, is a bit larger than the system has automatically recognized. We want to change that as well. Here's the mating surface. We simply say, okay, now we want to edit the bounding box. And now you see the bounding box where it's a slide attached to part. And now we simply grab that little arrow and pull the bounding box across the mating surface. Now we have the optimal size for our slider. And simply say OK and done. For ribs, same principle. System has recognized automatically ribs. We just pick a rib and the system shows us in our stock list where is that rib shown. If we think something is not correct, we can simply delete or zoom to the feature and have a closer look. If it is the one, that's okay. So we don't have to do anything. And the same applies for opening and inserts. System has recognized all the opening and inserts. Now we want to have a closer look at it. We simply click on one. And the system shows us, that is the opening which we have identified. And now we want to make that fit and shoot a picture of our part and import the data back to PCM. We import now the data. Now it's everything. It's now in the tooling system. You see here we have a comprehensive list of all the features which is NX has recognized. If you want to add something manually, simply do it by new. You can add the dimensions. Delete that again because we don't need that. Paste the image we just have shot. and we want to change this substance. We have a comprehensive list out of the box of substances. In that case, when we want to use a PA6 material, we just select that and say accept. And we have changed the substance. Now we want to go further down and see how the complexity in part surface looks alike. The parting line, for instance, it's a complex, normative is the standard. We have area with offsets, and we have an average for the free-form surfaces. Part quality is technical, and the ejector side should be stripped, and the nozzle side will be EDM structure. And we simply say accept, and now we have defined our geometry. Now you have seen how the calculation works with molding. I just want to show you how we do this with a stamp part. Same principle, we fire up a new calculation. So we're going to use a progressive die. The designation is prog die, and we see in the tool, we say simply accept. System is loading the data on the profile. We go to geometry. We're linking now the part and firing up an X. Here we go. And using now the stamping application of feature to cost, select the planar face. The orientation is in Z, which is correct. We don't have to change anything. We analyze now the body, and the system gives us the part dimension and the attributes. Has automatically recognized the bending areas. Now we want to combine the bending areas because it makes more sense. We group it. Changing to the other side. If we look at the trim areas where we have all the cutouts, in green you see the trim lines and the holes. We don't have a drawing and don't have an emboss area for that bracket, no needed. But if that would be a necessary, system would recognize, or if not, we can simply add it. Okay, tool specification and location. In Teamcenter tool costing, you have the ability to simulate different scenarios of sourcing. We want to show you schematically how you can simulate a tool price if you want to source it in Europe or in Asia, for instance in China. You are able to validate prices based on our out-of-the-box provided material and labor prices or your own standards. Now I would like to show you how we do that. Back to our part. Geometry we have done. Now we go to the tool specification tab, and you see the tool profile has 100 millimeters part, but our part is larger. So we have to change the profile, and I always say that is the brain of the system. It's 150 to 300 millimeters, and the system says, okay, I need a tool shop site. So change, or we select a tool shop site. We go to the Siemens site and say accept and save and hit calculate. And now it costs 78,500 euros. It's one cavity tool. And let's say we want to left and right, or maybe we just want to have a 4-cavity tool and see how much that costs. Hit the calculate button, and the system calculating automatically a 4-cavity tool, which is almost 205,000 euros. Now we want to know how much would it cost maybe in China. So I simply accept, calculate, and cost 132. Now we want to see the differences. Go to the Siemens side again, say accept, and you see you have a difference of 55%, which is quite a number. The system has automatically recognized the tool length, width and height, and the weight. We have a sprue system, a hot runner. We have 4 nozzles, and we have 1 gauge per part, but that can be changed. Tool lifetime right now is life equals lifetime. We can change it to number of a lifetime or service life in cycles. So we need 4 tools for over lifetime. We can add some tool maintenance. Let's say the average maybe 3%. And you can add, of course, logistic costs, custom charges, or other costs. On the other hand, we can add some additional costs, which we have in our knowledge domain. And here you can add your own knowledge, or you can use the one Siemens is providing. Right now we're using a date stamp. Use a date stamp for the run number and everything. Here we go. And simply by dragging and dropping, we add that run number, the date stamp, to our tool. Here we go. It's roughly 1,100 euros. Now I want to show you something about productivity factors for cycle times. In this slide, I want to tell you something about that. Tool manufacturers need to replicate an accurate digital twin of the tool shop to calculate realistic quotations. With this capability, tool manufacturers get the possibility to adjust cycle times of all manufacturing technologies, such as drilling, reboning, milling, turning, etc., etc. To achieve a more accuracy in the quotation calculation, meaning if you think a machine is faster or slower, you can simply change the productivity factor to adjust the time and consequently the cost. And I would like to show you how we do that. Now we have here our calculation again. On the left-hand side, you see our, for instance, here the Germany plant location, but it applies for every location or for any tool shop site. We're using, for instance, a drilling machine. And there's a DMC 635. We open that. Here's our machine. And the productivity factor is 0.3, which means is 30% fast, or it's 70% faster than calculated. And you can change simply the number if you think it's too low or too high, and has an instant result on your cost and consequently on time. For instance, if you're using the EDM machine, you go to the manufacturing step, and you see right now the productivity factor is 1. So we think it should be much faster or faster. Change it to 0.9, which means it's 10% faster. And you see this has already changed the hourly rate. Tool cost breakdown. In tool costing, we provide a standard Siemens cost breakdown, but of course on a request to add a customer CBD is always possible. And now I would like to show you how we using our cost breakdowns. Here's our calculation again. We go to the bill of materials, the stock list, so to speak. We open that. We have the basic design, cavity, functional units, and so on and so forth. And you can, of course, have a more drill down to the depth if you want to do that. You have your roughing, finishing, marking, polishing. And we jump to the functional structure, explain the function of the die, of the mold. We have the basic assembly, cavities, core features, special features, and so on. Let's say I want to change something, ejector system, for instance. Just open it, and I see here all my ejector types. And let's say I need a new one. New ejector pin, click on it, and add the length, diameter, and the amount. Or you want to change something. We have here a sleeve ejector. Maybe you want to change it. You can say, okay, it should be a two-stage ejector. Just click the box, make a check mark, that's it. Or you can change the actuation type, the system position, and so on and so on. You simply accept the change, and we are done. We can change the standard parts. Right now we have a Haskell plate, but you can change anything you want. And let's go now to the cost breakdown. Now I select the cost breakdown. Here we go again, before we selecting the cost breakdown, you see here all the processes, raw materials, purchase part, and so on. Let's have a look at the machining and the milling. The milling small. And we have here an hourly rate of 43.97 euros. Maybe that was a mistake. And so we want to change that, get the correct rate. Just click on it. And let's change it to 45. Say accept. And automatically the hourly rate changes, and of course the price. Now we want to publish that to our master data. Simply go in it, say change master data hourly rate, then it stays for the next calculations in our master data. And we don't have to change it again. So now we are selecting a cost breakdown. In that case, we're using our default, but as you see, we have many other ones which we have created. There's the standard default. And that is our standards default, which comes with the system. And you can save it, and it's an Excel file. Here you go. Now we want to show you the capacity plan. We go for the capacity plan, select it. Here we go. Chapter 1, say accept. Hitting the cost breakdown, export. And here's our machinery and capacity plan. So that mold is roughly 15 weeks on manufacturing time, and all the detailed hours are shown here with the hourly rates. So that can be used for the planning for the tool shop. Okay. You have seen the cost breakdowns, the capacity plan, and furthermore, you have now the possibility to import supplier quotes into Teamcenter Tool Costing to compare your internal calculation with your supplier or suppliers. I would like to show you that as well now. We have our calculation. We say we're in a new tool calculation. Again, injection molding. In that case, we say offer. Simply say accept. In that case, we don't want to have a parametric calculation. We want to use a cost breakdown import. We say accept. And now you see here we have now 4 tabs: geometry. Let's go further down. Basic data, geometry, tool specs, and cost breakdown. Now we go to cost breakdown. We select first the cost breakdown, our default again, and say cost breakdown import. We're using now the one from our supplier. Selecting then one, they open, and automatically is imported. Here you go. We have processes, hourly rates, and quantity, meaning hours. I know I want to compare that with what we have calculated internally. With a comparison cost breakdown. Now we open that up, pulling our calculation, our internal calculation against it. And now we can see our cost breakdowns, which we have created our own calculation, and the supplier's one, maybe compare cost by cost, maybe price and quantity together, and maybe the quantity itself together, and open that up. And now we can really drill down in the cost and quantity and see where are the differences. And now we have a base to negotiate with our supplier. Okay. What are the main benefits for tool makers or tool manufacturers with Teamcenter Tool Costing? We can decrease by using the system from 10 to 16%. That is a potential saving which we have reached with our customers with help of the tool costing solution we have. Working smarter, up to 50% in a reduction of time for the calculation. And of course, we have highly accurate quotations and the data is consistent. because we're using a common database. Important, I think, for me, one of the important points is saving institutional knowledge, preserving our valuable costing knowledge within the company. And last but not least, leading successful negotiations, enforce prices, keep accurate records, and act as a competent partner.
Thanks again to our presenter today, Mr. Peter Joko, and thank you all for joining. With that, the session is closed. Goodbye.